Thought we'd do some circles prep for Tamura. Tamura doesn't actually ask about circle theorems, well, ever, but it is in the specification, so it might be safe just to review and revise some of these ideas a little bit. Here are the 7 circle theorems that you learn at GCSE, and we'll be using all of them. Just have a quick look over, make sure you remember all of them. Otherwise, we'll get straight into the questions. I've got lots of questions to do because I really love circle theorems, so I didn't mind doing a bunch of these. I hope you'll enjoy them because they are good questions. You probably haven't seen very many of them before. Here's a very nice, easy one. We're looking for an angle x, for a length x here from these chords, length 3, 9, 15. Okay, so you could connect S and R and P and Q to make 2 similar triangles. How do I know they're similar? Well, because these 2 angles are vertically opposites, they're equal. This angle is equal to this one because of angles subtended from the same arc are equal, this rule here, and likewise this angle is the same as this one. So these are definitely 2 similar triangles, and so we can just find a scale factor. If we just put this one the right way up, like this, so that's just putting it like this way, and then put this one in the same kind of orientation, so red down here, black up here, blue over there. Scale factor is clearly times by 3, so sometimes something times 3 is 15, and we get x is 5. The reason that I'm doing this one first is because while you don't learn this rule at GCSE, some people in other countries learn a really simple and nice rule called the intersecting chord theorem, which is that if you have intersecting chords like this, A times D is equal to C times B. So here we didn't have to do any of that. We could have just said 3 times 15, which is 45, is equal to 9 times x, and so therefore x is 5. That might be worth bearing in mind, just in case they throw that in and expect you to do all that long way round working that I just did, whereas you can just kind of just boss it and just write down this and get it right straight away. On a similar vein, there's another rule that you probably won't have heard of, which is called intersecting secant theorem. So here's a question from a Maclaurin Olympiad, just from last year actually, I noticed. So that's cool. Prove this thing. So Tamura obviously won't ask you to do this kind of thing, but they could ask something like this because, like I said, intersecting secant theorem is kind of interesting. If you have 2 secants, this is a secant, so not a tangent that just touches it, but something that goes through it and passes through like this. If you have 2 of them, then then the distance mn times the distance mo, in this case, is equal to the distance mp times the distance mq. Which is kind of interesting, and well worth knowing because it can get questions like this done very, very quickly. The other thing I'd mention about it is that if you draw a tangent, tangents are just special cases of secants, right? They're just a special case that just happen to hit the circle only once rather than twice. So you can actually use this and say, well, if you call this point here something like r, you can just use mr times mr, because if you imagine bringing this secant down closer and closer to having one section point, mp and mq, the distances become closer and closer together until you get to the actual tangent point where this theorem just uses mr times mr. So that's kind of interesting. You can just use that here, and likewise it's also interesting that makes this a special case of the equal tangents theorem that you learn at GCSE, because you just get mr squared equals let's call this q squared, sorry, q's down there, but anyway, and you just square root. I'll show that just there in a second. Anyway, applying it to this problem, we have that AC times AP, oh, in fact, I think I'll do this little circle first. AQ times AB, so that's the secant here, AQ times AB is equal to AC squared, because this only touches this smaller circle at one place, so it's just AC times AC, which is AC squared. The bigger circle, AC times AP, is equal to AB squared, because B only hits it at one place. Yeah, and now I go ahead and prove that thing that I was talking about just now, which is that you have equal tangents. It's just a corollary of this theorem here, whereby MP times MP is equal to NN times NM, and then you just square root because they're all positive side lengths, aren't they? And you just get the tangents theorem that you learn at GCSE. So that's kind of interesting. It's just a special case of this. Anyway, continuing with this, as I was saying, you get that, you get this, which is what I said, AC times AP is equal to AB squared. And I think I literally just multiply these 2 things together to get that, and then you divide through and you do a Maclaurin Olympiad question very, very quickly if you know that theorem. Maybe that comes up to it. And the reason I'm saying maybe it does is because to prove this theorem is just using a bunch of circle theorems that you're supposed to know. So maybe Tamura will expect you to go that long way around trying to prove some circle theorems to get there, or using circle theorems to prove this to get there, and you can just write it down. So maybe that will come in handy. Anyway, what I'll do now is I'll do some proper questions, and we'll do them just using regular circle theorem rules. So I've shown you those 2 interesting rules, but now we'll do some regular ones. So from here on, definitely try these problems if you haven't already, and I'll do them as we go along. So okay, this first one here, we're looking for the length PR. I love this question because it's so simple. Like they give you nothing. So little information, and apparently you can answer this question. Draw in the center of the circle and do 2 lines into it. Now from double angular circumference to center theorem, this angle here is 90, and you are told that the radius is 4. Okay, and then to work out PR, we just have to do Pythagoras. So this question was very quick and easy to do, as long as you remember your circle theorems. And a really lovely basic question. I also like that you can do this a different way. You can just construct this angle here, and by equal angles subtended from the same arc, this is 45. But because it goes through the center now, that's what I chose it to do. This length is 8. This is a right angle here because angles drawn from the diameter are 90 degrees on the circumference. So we've got 8, we've got a right angled triangle, and we can just do some trigonometry instead of Pythagoras. Or we can just do some Pythagoras if we notice a nice isosceles triangle. That also works. Cool. Okay, anyway, this question, really love this question as well. Give it a go. It kind of looks like the cyclic quadrilateral thing, right? Except it's not a quadrilateral. It's, what is it, 1, 2, 3, 4, 5, 6, a hexagon. So can you turn this into a quadrilateral and then use the rule? Well, what if you broke it down like this? I think there are other places you could break it, but this is quite a nice one. Now we get two quadrilaterals, one over here, one over here. So we've got two equal angles, this one and this one. 95 plus something must be 180. That makes this 85, I believe. And then 140 plus something must be 180, so that makes this one 40. And then we just add those two results together to get our total angle of 125. Really lovely question, also from a maths challenge. Most of these are from maths challenges that I'll do first. This is a great question as well. Do give this a go. We're looking for this angle here. This is a circle with two tangents. And you've got this set up here, you've got an angle of 48 here. Now there's probably more normal ways of doing this question than what I'm going to do. But the way that I'm going to do it is we're going to I've just drawn it in GeoGebra here. And okay, so I can mess with it like this if I want to. But like the question is, where is this point? Right? Like where is that point? Is it here or is it slightly further down or further down still? Probably the easiest way to tell is by looking at this angle up here, which looks very close to 90. So maybe I should put this very close to 90. But that's not the point. The point is, I don't really know where this goes. And this is a really interesting strategy you can use, particularly in UKMT, but maybe it'll come in handy at the end of Tamura. If I don't know where to put this point, necessarily and logically, that must mean that this angle does not change when you move this point around. If they've given me no information as to where that point should go, other than a vague, terrible quality picture, then it can't matter where that point goes. This angle can't be changing when you do this. And that's just a logical conclusion that I have to draw. And so once you've drawn that conclusion within a problem, you can then think, well, if the angle doesn't change when I move this, because they've given me no information as to where it should actually go, and therefore I have no idea, why don't I just put it in the best place? What's the easiest place for me to put this that will solve the problem straight away? What if I put it all the way down here? Because then this becomes a 90-degree angle. This angle up, if I put it, manage to get it around the corner, that would be close enough. This is a 90-degree angle now. This is just half of 48 because I've got two congruent triangles there, and I can do the same thing over here. So that must be 48 halved. And so 90, 24, 48 halved, and I can just get that angle very easily. So that's a really nice conclusion you can draw here that gets that kind of question done very quickly. 180 take away the other two gives me x is 66, which if I go into the if I go into here and just click what is this, I should also get 66. And we can see that that angle doesn't change. I was correct. It doesn't change, and it can't do because they gave me no information about it. So that's quite a nice little trick you can pull sometimes on questions like that. Okay, so getting into some more thorough questions. This is also a Maclaurin Olympiad paper. Two circles, and they've given me things. Tamura obviously wouldn't say this. Tamura would say something like, find the value of A, B, and then give you a bunch of options. But anyway, let's get into it. So we've got a radius A and a radius B, so that's fine. We can label those up. These seem like the most useful points to draw my two radiuses because those are actually intersection points with the circles. We've got a length PQ, which is this distance here of 14, just down to there. And we've got a length AB of 16. Prove that AB is some number. So what can I find here? Well, what if I connected, well, these are all 90 degrees because, of course, tangents and radiuses at 90 degrees, of course. What if I connected the two centers? I've actually got a trapezium here, right? Because of these coherent area angles making these two things parallel. So I've actually got a trapezium here. Base 16, height A and B. So that seems vaguely helpful, but not too much right now. Now, what's the other construction I've got going on? Well, I've got a B here, 90 degrees down to a 14, 90 degrees across to an A. And as soon as you see this structure in math challenges, but maybe it will turn up in Tamura, you should be rejoicing because you can solve this kind of structure and you can find the distance across, which happens to be the same distance across as that height of the trapezium, which seems very useful. But I can work out that because this is a nice trick. Just watch. and we make a lovely big right-angled triangle that I think I can solve. 14 squared plus a plus b squared square rooted is this red length, which I can just shove into there. So I haven't quite solved it, but I've made some progress here, and I think this looks good, because if I just put the 16 there, this length here is b minus a, and now I can do Pythagoras again, and maybe this will work out. So this squared, where's that 16 plus this squared is equal to this squared, but that you just remove the root, right? Lots of things should hopefully cancel here, and they do, which is nice, and you get AB is equal to 15. Really lovely question, that one. This is a lovely question as well. I can't remember whether I wrote this question or whether I found it and then just put it in GeoGebra. Square is area 1, so find the length A to E, which is this diagonal length here. This is a semicircle here, if it wasn't obvious. And this is a tangent to the semicircle. Okay, so area 1 means the length is 1 and 1. You can call this little length ECX, which makes this length 1 minus x, because this length is 1. But of course, equal tangents from circles mean that if this distance is x, this distance is also x. But likewise, equal tangents intersecting from circles means that if this distance is 1, this distance is 1. And the question is very straightforward from here, because you've got a nice right-angled triangle. 1 squared plus 1 minus x squared equals 1 plus x squared. And that should solve for x, because things cancel, and you get your answer. Of course, we're not looking for that. We're looking for AE, but that's just 1 plus x. That's going to be 5 over 4. Good. I did write this question, and I'm really proud of it. So do give this a go. I think it's a super sneaky, great question. Although I'm sure people will come up with solutions that aren't as sneaky as mine, and the whole problem will be slightly less interesting. But anyway. Arc BC is 40% of the circumference. Now what that means is if you draw to the center, and I gave you the center to be helpful, if you draw to the center, this angle here has got to be 40% of 360, because the circumference is directly proportional to the angle that you use. So 40% of 60 is 1 for 4. And now this is the sneaky bit. Draw a line from A to C, and can you see it? Do you see it yet? You've actually got double angle from center to circumference, because this angle here is drawn from A and C, and B is on the circumference. This angle here drawn from B and C from the center. So you've actually got, it looks very sneaky, but this angle here is half of 144, which is 72 there. And now we also have that AD is a quarter of the circumference. So do the same trick down to 0. This angle here must be 90, because again that's a quarter of 360, which means that, again, being super sneaky, if that distance connecting A and D to the center, that angle is 90, A and D connected to the circumference, this angle here between the grey line, that's 45, just up to the grey line, because it must be half of 90. And now for removal of the fluff, this is just a triangle. 180 minus the other 2 gives you this. That means this is the same because they're vertically opposite. Add those together, take 360 away, divide by 2, and we get 117. This is x is 117. Really lovely question. Although I know that I did that. Anyway, cool. This is actually from the Pearson textbook. It's one of the challenge questions. So now we're moving away from circle theorems and doing some circle on graphs questions. I'm only doing a couple of these. One of them is going to be from Tamura. This is quite a nice question. It's very Tamura-like. I could definitely see this being written in a paper as one of the first kind of 10 questions, I think, in paper 1. You've got a line here. You've got a circle radius root 5, center 7 minus 1. I thought about doing this entirely graphically, but couldn't quite get it to work. And I think I was going to get it to work, but then realized algebra is just much easier. The line is y equals mx minus 2 because the y-intercept is minus 2. Just shove that into there, and when you clear that up, square out both sides. This becomes just an mx minus 1, so it expands to that. Clear up both sides and group the x squared and the x terms. There should be an x there. Apologies. There should be an x there because I'm grouping x terms. I just forgot to type an x. This equation, this circle in this line, should meet at one point, which means the discriminant of this quadratic should be equal to 0. So that's A, that's B, and that's C, because there should be an x there, as I've said, which means I can just put those all in for that. Expand that out, and we've got a new quadratic. We solve it up. This looks horrific, but everything is divisible by 8, which is very fortunate. And this, again, doesn't seem that easy to factorize, except it is, because the only thing that makes that is 2 and 11, or 1 and 22. The only thing that makes this is 2 and 1 with some nices, and it doesn't take that long to figure out this. M is positive, of course, because it says so. And so 1/2 is going to be the answer. Very Timur-like, I could see that on there very easily. This is actually a Timur question, because of course I couldn't get through a whole video talking about tangentially related to Timur. See what I did there, tangentially? Anyway, I couldn't get through a whole video without talking about the value of sketching. So you can do this algebraically, but it's much easier to sketch it. We've got one circle radius 8, center -4, -1. And we've got another circle, center 8, 4, so up here somewhere, radius r. Now these two circles only meet at one point. How is that possible? And how is it possible to have two values of r? Well, the sketch will tell us, right? The sketch will tell us that the only way to do that is to have a circle that looks like this, where they just meet like this, or a circle that looks like that, where they meet over here. Those are the only two options, and a sketch told me that straight away, and the sketch is going to tell me how to work out both those things very easily, because that distance is 8. You can work out the distance between the centers very easily. It's just going to be the distance x distance and y distance, do some Pythagoras, and you very quickly and easily get that r, what have I, oh sorry, yeah, 12 squared plus, you could expand this out and do a quadratic. Much easier to spot that 12 squared plus 5 squared is 13 squared, which just makes this 5, because 5 plus 8 is 13. So yeah, knowing your Pythagorean triples helps out there. What about the other case? Same kind of deal here, just the other way around. The distance for this whole distance is r, and you know the distance between the centers we just worked out is 13, or you could call it r minus 8, I guess. Yeah, sure. Yeah, I mean, you can see what I'm doing. R is 21, and you just take away these two values and get 16. So those are all our circle questions. I hope you enjoyed the video. I certainly did, because I love circle theorems. But yeah, sure.